Building a microservices application is a lot like playing a game of Jenga. Each piece represents a critical component of your system, and you need to carefully allocate resources to keep everything balanced. But just like in Jenga, if the load is not distributed properly, the entire structure can come crashing down. In a microservices application, each pod is designed to handle a specific amount of load. But when the load exceeds pod's capacity, it becomes overloaded. This is where auto-scaling comes in. By automatically allocating additional resources, we can ensure that the system can handle increasing demand without overloading. However, this comes with a cost, which is the energy and performance trade-off. The more resources we allocate, the more energy the system uses. And when that energy comes from high carbon intensity sources, the environmental impact can be significant. So, here's the big question. How do we strike the right balance? How can we maintain high performance while minimizing energy consumption and reducing our carbon footprint?
When searching for the answer, we discovered that most research focuses on resource-efficient autoscaling, but there is very limited research done for carbon-aware autoscaling. Moreover, not much research has been done to balance this trade-off. To research this topic, we need a microservice application and a set of tools for monitoring and load testing. For the application, we chose the benchmark called train ticket. For load generation, we used Locus to simulate workload. Then, with Jigger, we analyze microservice call hierarchies, which helps to capture the dependencies between services, and Jacoco for coverage analysis. Next, we capture resource metrics with Prometheus, energy consumption from Kepler, and carbon intensity using the WattTime API. The data is stored in a metrics database. The core of our research is to experiment with machine learning models for autoscalers. By experimenting with various ML models, our ML-powered autoscalers predict when, what, and how to scale, ensuring high performance while minimizing carbon emissions.
The train ticket application can be represented as a graph structure, where each node represents a microservice containing features such as CPU, memory, and energy consumption. These features can be collected and processed as feature matrices that vary over time. On the other hand, the edges of the graph represent dependencies or connections between microservices. From this, we can construct an adjacency matrix of microservice nodes. One challenge we face here is that microservice dependencies vary across both time and space. To address this, we experimented with a spatio-temporal convolutional network as a machine learning model. The feature matrices and the adjacency matrix that we built earlier now serve as the inputs to the model. The model consists of spatio-temporal blocks and predicts the optimal pod count. And here's a quick look at a spatio-temporal block. We also addressed the response time versus energy trade-off by incorporating carbon intensity data. For example, when the carbon intensity is high, the model sets a higher threshold for deciding whether to scale up a microservice. This means that only microservices with extremely high probabilities of requiring scaling will actually be scaled up. This is one of the autoscaler models we experimented with, and we have more to explore.
Let's discuss the results. HPA always performs the best, keeping the response time as minimal as possible. The STGCN approach is dependent on carbon intensity. Here in Poland, having more carbon intensity, the scaling up is more restrictive and hence you see higher response time. Whereas in Finland, having less carbon intensity, the scaling up is less restrictive, hence we see lower response time. Let's compare the carbon emissions of our application. In Finland, replacing HPA with STGCN, we can reduce carbon emissions by half. In Poland, the impact is even bigger. Replacing HPA with STGCN reduces carbon emissions by 3 times.
Sustainability isn't just a buzzword, it's a necessity for the future of cloud computing. Our intelligent scaling approach addresses the trade-off by minimizing carbon emissions while keeping applications fast and responsive. This is a step toward a more sustainable cloud ecosystem, one where efficiency and environmental responsibility go hand in hand.